Welcome back everybody to another video lecture. We're still talking about programming PLCs, and I wanted to show you this document. This is on or will be on your Canvas. This document is about entering ladder logic. I'm not going to talk about it, but I do want you to at some point go over this, preferably before you start working with your simulator, which will be next week. So I just wanted to make you aware of this document. And then there's one more that I'll bring up here in just a second. Okay, and this is the second document on program files. So if you take a look at this, this won't mean a whole lot to you right now. This actually was referred to or reference from one of the other PowerPoint lectures we did a couple days ago, and it said to refer to a handout, and this is the handout on program files that was referenced. So again, this won't mean a whole lot to you. Your simulator is based on this SLC, they call it the SLC 500 controller by Allen Bradley. So it looks very similar to the Allen Bradley SLC 500's PLC. And this structure right here, this file structure, is what's used in the Allen Bradley, and it's also what's used in your simulator. So when you get your simulator, I'll refer to this. I'll show you where these files are. So I would just say have a look at this right now. Just kind of be familiar with it. You don't have to memorize any of this, but just kind of look. If you look here and then the data files, just kind of read the names and be familiar with it. And when you use your simulation software, I'll point this out to you. You can actually see where these files exist. You'll see these in your software. So I wanted to point those two documents out, and now we'll continue on with the PowerPoint presentation. Okay, so here is the PowerPoint. This is called function chart programming, and so for the last couple lectures we've been talking about programming the PLC, and you looked at several instructions for programming the PLC using a language called ladder logic. And so this will introduce you to review ladder logic. We'll talk about several other ways to program, but the focus of it is this idea of function chart programming. So the purpose of this video is to explain what that is and give you a glimpse into how it works. So the three most common ways to program a PLC: ladder logic or relay ladder logic, which we've been talking about. You can actually program certain PLCs directly using Boolean instructions or Boolean language, and then this function chart programming, which is somewhat new compared to the other two. Here's a hardwire circuit, a very simple control circuit, and let's say you wanted to implement this in ladder logic. You have a normally open push button, you have a couple control relay contacts, one normally open, one normally closed. You have a limit switch, LS1 is a limit switch, and SOL is a solenoid. And so that's your output. If you want to implement this in ladder logic, you would use the instructions that we talked about previously. And so I can implement each of the buttons and or contacts. Any input is shown as a examine if open or examine if closed instruction. And so notice here we basically translated this is a physical contact, normally closed contact, and we're representing that down here as that representation is examine if open. Now remember our discussion in the last video about logic continuity, so this might not necessarily translate this way. It depends. You have to understand the circuit, the logic of the circuit, to actually do that. But assuming that it does, then this is what you'd have as a ladder program. Notice the addresses here. The addressing is pretty important. That's the way we map the actual instruction to the screw terminal and the actual instruction to a position in the input image table, or in the case here, the output image table. And so this is the way you would implement this in ladder logic. Some PLCs will allow you to implement directly using the Boolean language, Boolean algebra. And so here's the same circuit, and this is just kind of a general schema here of the way you might do it in Boolean algebra. if you notice, the push button and the control relay contact, A and B, that's AND logic because they're in series, and that AND A and B is ORed with C. And so if I look at the Boolean expression, I got A and B. This parentheses just says that you can kind of view them as one unit, one thing. That A and B, the whole thing of A and B is ORed with C. And then this, which represents everything here, is ANDed with D. And notice that's a normally close contact, and so we have to knot the D. And our output is Y. So if I wanted to implement this hardwired circuit as Boolean language, this is what I would come up with for the Boolean expression. Some PLCs allow you to enter this directly into the CPU. And so here's a generic way it might be done. Start PB1. It says the AND this, AND PB1 with CR1. So they're ANDed. And then OR that with LS1. So that takes care of this. It's OR, LS1 is C. Now you might wonder, well, wait a minute, I don't have any parentheses down here. Well, if you remember from before, we talked about order of precedence, like order of operations. And so you really don't need, like, I can take these parentheses away if I wanted to, because ANDing has a higher precedence than ORing. So even if the parentheses were not here, the processor would know to AND these first and then take the result of that and OR it with C. And so I don't need any of that over here. And then so I OR, and then I AND it again. It says AND, it's a knotted, D is knotted. And so notice here I'm using the actual addresses here. These switches names represent the addresses. So you could do something like this. Again, this is a generic way of doing it, but each manufacturer that allows this type of programming will have a specific language or specific way or style that they use for their Boolean expressions to be entered into the PLC. So that's two ways. One you're becoming more familiar with, ladder logic, which is what we'll do, and the other Boolean expression. I haven't seen a whole lot of that. Just know it exists, and if you had to do it, you could do it. The learning curve would be not too steep. So this kind of ties the three together, or the two together, just to review. The hardwire, the ladder program, and the Boolean expression. Well, there's actually another way that's really gaining traction nowadays. This is called function chart programming. Function chart programming. Sometimes they'll abbreviate that FCP, function chart programming. And so I won't read the slide to you, but this was developed in Europe. It uses what they call a more structured approach. And so you'll see what I mean by structure. This is nice. It's a pictorial representation of a control process. So it still uses elements from your regular ladder logic. You still use it, but you add structure to it. And by structure, what we mean is it's more like flow charting, and then each shape in the flow chart will be represented with some kind of relay ladder logic. So again, we'll go into that. This idea of function chart thinking. I'll pause for a second and allow you to read this. And I want to read the first part of it. So this idea of function chart thinking, you want to remember that, function chart thinking. Any process or machine, no matter how complex, can be described as a combination of sequential and or parallel events. Now that's pretty important. You can take the most complicated process that you can think of, and it can be divided down into just some simple, either sequential or parallel events. And function chart thinking or function chart programming takes its cue from that. The overall program or process can be complex, but the individual events are often quite simple. And that's true with any kind of complicated device. With function chart programming, you divide the process into sets of simple steps instead of creating one long ladder logic program. And that's the power in this. And again, when I show you here the next slide, then we'll talk about what I mean by that, the power in this. So here's a function chart example. The list below shows sequences of steps involved in a simple machine process. So let's say we're making this, I don't know what you want to call it, a widget or whatever. So here's the unstamped part, here's the unprocessed part, and you're going to go through these steps to end up with some kind of product at the end of the line. Notice how this is listed out in these steps. So this is the steps it takes to go through to go from this to this. The operator presses the start switch to start the machine or to stop the machine. The machine checks for a part. Well, how would it do that? Well, there must be some kind of sensor. There's different sensors you can use to check for the presence of something. The machine checks for a part. If the part is present, the process continues. If it's not present, the conveyor moves until a part is present. So there you can see some logic there. Some decision has to be made to tell if the part is present or not present. The part is then locked in place with the clamp, and once it's locked in place, the press stamps the part. And once that's done, the clamp is unlocked and the finished piece is moved out of the press. And then the process continues if the machine is in one cycle mode. The process stops if the machine is in one cycle mode, or it continues if it's in continuous cycle mode. So here's what happens. Each one of these steps becomes basically a little mini program. So they have this, I call it a flow chart, but it looks kind of like a flow chart. You can see step 1, I have it written here, wait for part. Step 2, you got to check for the part. Step 3, lock the clamp. Step 4, press the part, and so forth. We can go through all the steps. If it's in continuous mode, this thing will go around the loop this way, continuous. If it's in one cycle mode, then it'll wait for you to press start again. And so, as I said before, each one of these becomes a little mini program that does just one or two things at the most. And the beauty of it is each program, each part of this, each step will run by itself as if nothing else was around it. Now, you might not see the power in that, but it turns out to be really, 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 really powerful for a couple reasons. Reason number one, you can take a step out, and you can, if you have to work on it or change it, because this is a program all to itself, it doesn't affect parts in the other parts of the program. If you think about ladder logic programming, you can just write one long ladder rung, and as you'll learn in a couple weeks, you're actually able to, there are instructions that you can use to jump around the ladder, to move to different parts of it, to move back and forth in the program. And so you can actually make an adjustment early in the program that can have an unexpected effect in other places in the program if you have a lot of lines of code. So with function chart programming, since each individual step is its own program, it makes maintenance a lot easier. Also, there's this idea of reuse. If you want to use, say, step 3. Step 3 is its own little program. If I want to use step 3 in another program, well, since it's its own self-contained program, I can basically use that in another program or somewhere else in the main program. I can use it over and over again. And so function chart programming, this idea of using the structured programming approach, is actually very, very powerful. Other languages use things like this or ideas like this. If you know any other programming language, sometimes they'll refer to these mini programs as a procedure. In some language they call it procedure. Sometimes they call it a function. So this is already done in normal programming languages, and this is just applying it to PLCs, this idea of function chart programming, and using these steps as I'll call functions for now, but that might be a bad word to use because functions are actually used in other places with PLCs. This is what I mentioned before. Once you get the list of how the process works and you understand that list, each part of the list becomes a little mini program. Now this is important. Processors that support this type of programming understand which part of the program are active and only scan the active steps. All other steps are not scanned, thus reducing the program scan time. In a previous video, we talked about scan time, and we talked about effects of scan time. If you have a switch that's operating faster than the PLC scan time, it can introduce errors. If you have counters or timers that's working faster than the scan time, that can cause problems. But here, imagine a really, really long program. The way the PLC scans through it, if it uses horizontal scanning, it has to go through every line of code, even if that particular line of code is false. It has to go through it to determine it's false and then go to the next one. And if you have 1,000 lines of code, 1,000 rungs, that can take a little while. With this type of programming, function chart programming, the processor knows which part is active and which part should be skipped over. And so it'll go right to the active part, which allows for increased speed. It reduces the scan time a whole lot. And then there's this idea of an interlock. So let me say a little bit about an interlock. There's physical interlocks and then there's software interlocks. An interlock is can be as simple as I might have an off-on switch, a main switch in the factory that's I can put a padlock on so that I can keep someone from turning it on. Basically, an interlock is a way of preventing something from happening. So one way is to use actual lock and pad, maybe a key lock. Other ways to use a password, maybe have some kind of keypad password. There's a lot of ways to do that, but in general, interlocks make sure the process executes in the correct order and making sure something doesn't happen. So for example, let's say I have an elevator motor, a dual motor that can either raise the elevator up and there's a button to go down. What I don't want to happen is for both parts of the motor to energize at the same time, up and down. That can cause an issue. And so you can have a interlock. You can have circuitry that guarantees that you can either go up or down, but there's no way that both conditions can happen. So interlocking turns out to be very important, and a substantial amount of the logic could go to software interlocks. But with function chart programming, it's not an issue because the processor does not scan the parts of the program that are inactive. It doesn't need as many interlocks. In some cases, you can even eliminate the interlocks. And if you do have them, they're a lot less complex. This idea that troubleshooting is also much easier. That goes back to the idea that because each part of the program is an individual program all to itself, we call that, in some areas they call that modular programming. If something is a module, that module can be just kind of taken out and replaced with another module. And so you can think of it like that each part of the program becomes its own module, and if you need to make an adjustment to it or change it, you can easily remove it, and as long as you replace it with something else that's working, the rest of the circuit shouldn't be affected in any negative way. This mentioned here, I won't read this slide, but this slide mentions Allen Bradley. They have their own genre or type of function chart programming. So now what I want to do is get into just some general symbols for this type of programming, function chart programming. The very first symbol, the basic symbol, is called a step. So a step represents an independent machine state. Notice the symbol here. The symbol This is a step, and that's just the box here. That's the box. That line down here represents something called a transition. That's not part of the step. But you got to use a step and a transition together, even though they're two separate things. So imagine this symbol in front of you. When you click on it, it opens up a window, and you're able to put a small program using ladder logic. You're able to put that in the box. This line right here represents a transition. If you double click on that, it opens up a window where you can put code in there using ladder logic, the symbols that we've shown you in other PowerPoints. You can put the ladder logic in for the transition. Now, what is this step in the transition? Well, the step is the actual process. It would be, it could be one of these. It could be. But it's the actual process that you want to go to or through. The transition is a part of the code that says if it's okay to go from one part of the program to the next part of the program. And so, let's say you double clicked on this. Now, this is a really kind of silly program. You can have many lines of code inside of here. But here, I go inside of here and I have, well, the fact that I don't have an instruction here means that as soon as this is run, this right here automatically is true. It turns on because this is a non-conditional run. But when this turns on and we scan this next line, if this is true, then it'll turn this output on. And so you can imagine other lines of code, other rungs here. Once you go through whatever this program is doing, once you go through it, when it gets to the very end, it'll go to the transition, and the transition says, is it okay to go to the next step? And if the transition is true, it'll leave this step and go to another one. If it's false, it'll go back to the beginning of this and run it again. It just continues to run in the loop until the transition says it's okay to go from one of the little mini programs to another. So maybe I have some kind of sensor. Let's say I was building a car and I have some kind of machine maybe mounting the bumper, and then another robot coming in and actually tighten the screws down for the bumper. And then I want to know, is it okay to go from the bumper, maybe the left side of the bumper to the right? Is it okay to transition from one side to the other? Or maybe if I'm done with the bumper, from one vehicle to another. So I have to have some kind of sensors or devices to let me know if whatever the function of this is, that code, if it's done, then I can leave this and go to the next one. So it's the job of this transition code to check to see if whatever thing has to happen here, if that's complete. And if that's, yeah, it's complete, okay, it's okay to go from this box to the next one. If it's not complete, it'll rerun that. So the step is the simplest, we'll call it, I don't want to call it instruction, I'll say structure. It's the simplest structure you can have in this type of programming. This says a little bit more about the transition. I mentioned that if you clicked on this, then you can put code in there. So whatever, these are checking something. Maybe they're checking the presence or absence of something. But if these are true, and it's okay to transition out of this step, then it'll go to the next step. So the transition and the step are used together. Also notice the number here. There's a number there, and then notice the transition has a number. You can think of those as being very similar to addresses. You got to have a way of referencing the step or referencing the transition, and so these addresses are there. So the step and the transition. Well, what you can do then is start to build from there. I can have multiple steps and transitions together. And when you do that, it's called a simple path. And so what happens is you fall down here into here, you run this ladder logic, whatever it is, you run that code, and then you check to see if it's okay to transition out of number one. If it is, if it is not, it'll go back to the beginning and go through it again. If it's okay to transition from 1 to 2, then if this is true, that transition is true, it'll go to the next one. And it'll keep doing that all the way down to the end. So a series of steps and transitions is called a simple path. So you can kind of see what we're doing now. We're taking those basic symbols and we're making more and more complicated structures. We'll call them structures. So each step in transition is a file. Each step in transition is a file. First step of function chart programming, this SFC is using a different terminology from Alan Bradley. The transition, and all the transitions are labeled. So simple path, pretty simple to understand. Well, then we can go to something called a selection branch. A selection branch. The selection branch, you can think of it as being equivalent to an OR. In the sense that with the OR, if any value is true, then the whole thing is true. Well, what this does is, let's say that I had some other code here, maybe that simple path, and I've fallen down and transitions to each one of the steps, and then I finally end up in this step. Now what happens in this step is, this will actually go to this first branch and ask and see if it's okay to transition into this branch. If it's not, it'll go to the next branch and then to see if it's okay to transition to this branch. If not, it'll go to the next one. It's looking for a true here to say it's okay to go into that particular box. If the true is all, let's say it's all the way over here on the right and everything else is false, you see it's going to take time to test each one of these to see if it's okay to enter into that step. And so here it's going to take the first true one. It'll do that first. So if you're actually programming with this, the thing that's most likely to be true, you want to have that more to the left. You don't have to do it that way, but you can reduce your scan time if the event that's most likely to be true is further to the left if it scans from left to right. The next structure is called a simultaneous branch. So this is equivalent to, logically equivalent to an AND. So what this does is it allows you to run parallel paths. All the parallel paths are active at the same time. So you have to have at least two paths for this to be the simultaneous branch. So here's an example of how this might work. This is a practical example. So I'll give you a second to read this and then I'll talk about it. And by the way, PCB, that stands for printed circuit board. So a PCB is a component that you mount electrical parts to. And so you have PCB1, printed circuit board 1, printed circuit board 2, and then you have a third one, the motherboard. So maybe you're putting together a computer. Assume that you are mounting parts on printed circuit board PCB1. So you're mounting parts on one board. At the same time, you're soldering on the second board. And then the motherboard is waiting, it's finished, and it's waiting for the other two boards. You got some kind of machine that's going to assemble these. The only logic scan is a logic for mounting parts PCB1 and PCB2. And the reason for that is the motherboard is already done. It's already went through the steps to create the motherboard. So there's you can think of three things, three branches, three steps, three sequences. Well, that one third one, the motherboard, is already done. So it's going to wait. It's not going to transition. It's just going to wait until the other two branches, the other two events are true. If you look at this pictorially, it'll make more sense. So this is the actual structure for the simultaneous branch. So notice it kind of looks like the OR, but it's actually different. So here's how this works. If it's okay to transition into this structure, then all of these, this line right here represents logic flow to all of these at the same time. And so this is going to transition to each one of these. Now this one we said was already done. There's only a few steps here. So place the motherboard on table, mount the edge connectors, and it's done. So now this is Spark right here. This is all true, so it's done. It's Spark right here, but nothing can happen until each branch is true. So while that's waiting, we're going at the same time we're running through these steps right here. So place the first board on the table, mount the parts, cut the leads, adjust the pots. Pot is a potentiometer, variable resistor. While you're doing that, on the second one, you're mounting the parts, you're soldering solder mask, cutting the leads. Once everything is done here and all three branches are true, then we ask if we can transition out of this whole structure. Notice each individual, the last step of each individual branch, you have to transition out of that. If it's not okay to transition out, it'll wait in here or just keep repeating, looping until this is done. But when each one of these is transitioned out, now I don't know why this is interesting that we transition into here. Once we're done, we don't need to transition out of that. Once that's done, it's just waiting. So it's interesting they don't have a transition here, but we'll take it for what it is. Once all of these branches are true though, then we can transition out and the assembly takes place. So the idea here is all of these have to be true in order for this structure to run and for you to get through the whole structure and transition out. So on the previous structure, this one, we were looking for the one most likely to be true. If you put that one first, if I have 1,000 of these and the true one was in the last place, I have to go through all 999 before I get to the one that's true. That's why I said you want to put the one that's more likely to be true further over to the left. Well, here it's a different situation, because if you put the one most likely to be false, if all of these are true, it's looking for the one that's false to go through and to become true. So you would have the one most likely to be false. I would put that further to the left. You don't have to do it that way, but we're talking if you have a really long code using a lot of these structures, a really long program I meant to say, then you can actually gain a little bit of scan time by just doing these little tricks. So, but it'll work either way. So make sure you understand the logic of this, the logic of it. And then of course there's advantages to this type of programming. So I'll be familiar with these advantages of function chart programming. We'll go through it. Function chart programming allows the description of the problem to become the actual program. So you remember in the first couple slides where we had the problem, where we were making the widgets, and we had to actually list out the steps. The listing of the steps, each step became kind of a mini program. So just understanding the problem helps you design the program. So that's a big advantage. Transition logic ensures that only the appropriate section of the program operates at any given time. We've already mentioned that. That can save scan time. I skipped this one. It says it aids in the understanding and localizing of problems, so it's easier to troubleshoot. If you understand how each mini program works, each step, then if you have some kind of issue, if you really understand the system, it's easier to isolate the problem. And troubleshooting when you have a lot of lines of code can be a big deal. The programming is simpler. I think it's simpler because it's more structured. So it's not that the code is simpler, but it's more structured. Just when you put things together in modules and pieces, it makes more sense. Faster scan time for several reasons. One we talked about was you don't need as many or as complex interlocks. It's easier to maintain, so if things are modular, they're usually easier to, if I have to change something or update something, I can go right to one part of it and do that. And for the same reason, ease of future enhancement. This is some other variations of programming languages that you can use for PLCs. State diagrams, I won't go into that. That's a big digital thing. BASIC is a language. I think it's beginners, all-purpose, symbolic, instruction code. It's been like 20 years since I've seen that, so I think that's what that stands for. But just know that's a programming language. C is also another programming language. These are all called high-level languages. It says, and there's some other high-level languages. A high-level language is just a computer programming language that uses English-like words, as opposed to ladder logic, which is a symbolic language because you use symbols to represent an instruction. So for that's it for function chart programming. And for the programming in general, these last couple lectures was just kind of meant to kind of introduce you to the symbols and this part of the instruction set, and looking at these ladders. And now what we'll do in lab, you'll ease into the actual programming of the PLC using the simulation software. So guys, thank you. Have a great rest of the day. And if you have any questions over the material, you know how to reach me. See you soon.